Today we're going to do a review. Next class is a midterm. I have a whole bunch of problems, but do you have any questions first? No? 7-1. Actually, 7-1 is the same as the problem number 3 that I was going to do today. So we can go to that.
Are we getting into the probability of error?
No probability. Okay, so let me first, you've received an email, right? So the topics are Shannon capacity formula for AWGN. That's the one that we had on a previous exam. You didn't do quite well there. So, but I cannot let you leave the class without knowing that point. Because it's such a fundamental equations for us in digital communications. I have to make sure that you understand what it means and how it's used. The next stuff is all of these manipulations going between signals and vector space, representation of signals in the signal domain, time domain, and vector space domain where we decompose them along the basis vectors of the signal set. The notion of the dot product, the notion of the norm, the notion of orthogonality, linear independence, all of these things might come into play. Gram-Schmidt orthogonalization, we did a couple examples here. You've had some for homework. One-dimensional, two-dimensional signaling, pulse amplitude modulation, PSK and QAM. Now, we didn't do probability of error, so it's going to be mostly these linked to the vector space topics. Like, for example, I may give you a constellation and ask for the Euclidean distance between them, dot product between two constellation points, and so on. Right? So it's relatively easy, but you have to know what you're doing. It's not easy if you don't know it, I guess. The next thing we cover is correlating receiver and meshed filter. And there are a couple of things there. I want you to know how to draw impulse response that is matched to a signal. What is the signal to noise ratio at the output? You know, how you calculate that, and you can do that, by longhand or just remembering the fundamental result that we derived in the general case. What is the signal to noise ratio output of the matched filter?
2 over N.
2 epsilon S over N0, yeah. So that is a good formula to remember. And the last but not least is basic concepts in probability. What I just came after grading comprehensive exams, and I noticed that some students managed to get all their exams passed, and they're at the end of the master's degree in electrical engineering, and still have some issues with PDF, CDF, mean standard deviations, and so on. So from this point on, and we have it on record, it's going to be part of every single exam. There will be a little, problem that requires you to calculate something using PDF and CDF, some expected value or something. Right? I have to make sure that you know that, because that's such a vital tool to us that you guys need to know it. It goes without saying that you know how to do basic concepts in probability, just like I'm testing addition and subtraction and square root at every single exam, right? Without saying. So expect that some of that would be on every single exam. So let me look at that problem. What was 714, and then we'll go through the.
When was that assigned?
Signed yesterday.
Additional problems.
That one's fun.
All right, so this is a typical problem, right? All right. So this is 714. It says antipodal binary communication system employs signals as S of t that looks like this. This is T. This is 1, 2, 3. So this is S of T. So it says sketch the impulse response of the filter matched to S of T. So how does impulse response of the matched filter look like? How do we generate impulse response of the matched filter? We know that that h of t is going to be S of capital T minus T. In this case, this is capital T, right? So you're going to be sending, this is your entire signal. So the impulse response of this filter, I'm going to take this, flip it over, right? So let me do first step. First step looks like this. This is T, flipped over, right? So this is minus 1, minus 2, minus 3. And you take this and delay it by T. So in the second step, you delay it by T, and you end up with this. This is your h of T. Do you notice something funny in this particular case? H of T is the same as S of T. It doesn't have to be that. Just be cognizant of that. Now, so that's part A. Part B, it says, sketch the output of the matched filter to the input S of T. I'm going to do this. I'm going to say S of T is going to be pi of T minus 1/2 over 1 plus pi of T minus, what is this? This is 2 halves, 4 halves, 5 halves, right? T minus 5 over 2 over 1, right? So that's my S of T expressed in terms of the pulse. This pi signal is the pulse that is delayed at 1/2. So it's centered around 1/2 and the width of the pulse is 1. And this one is centered around 5 halves and the width of the pulse is 1. The h of T is the same thing. So let me write it. So it's T minus 1/2 over 1 plus pi of T minus 5 over 2 divided by 1. So y of T is going to be S of T convolved with h of T, which is pi of T minus 1/2 over 1 plus pi of T minus 5 halves over 1 convolved with the same thing. Pi of T minus 1/2 over 1 plus pi of T minus 3 halves over 1. Right? And now, what you need to remember is that pi of T over 1 convolved with pi of T over 1 is lambda of T. In other words, if I have signal that looks like this, and I convolve that with another signal that looks like this, so this is minus 1/2, 1/2, and this is 1/2 minus 1/2. So this is pi of T over 1, and this is pi of T over 1. And when I convolve the two, I get this is, what is this? 1 minus 1. Right? So if I convolve two square pulses, I get the track. Right? And now I'm not gonna, you know, it's a lengthy process, but you can see here you have a lot of square pulses to convolve. You have this convolution with this convolution with this one, and so on. What you need to make sure that you have appropriate delay. For example, this one convolved with this one will result in lambda that is delayed to 1, right? So this is going to be pi of t minus 1/2 in convolution with this pi of t minus 1/2 is going to be lambda of t minus 1. Right? It's going to be the lambda signal that's delayed. And then, you know, you kind of go pair by pair, and then you get all of these lambda signals that are convolved. So that's the output. 3. Determine the variance of the noise, I guess, of this missing, the variance of the noise, the variance, the noise of the output of the mesh filter at t equals 3. Okay? And then the last one, you can skip it because it's probability of error. We haven't finished that.
Sir, that should be t minus 5/2.
5/2. Now, for the variance of the
Is it asking the variance of the noise of the output?
the output yeah, variance of the noise is the output of a matched filter. The variance of the noise. First, we have this, right? We have expected value of the noise, and the output is what? If I have a zero mean Gaussian noise. It's zero. Right? Now, so expected value of n squared is what we are actually looking to determine. So, think if there's a shortcut for this. Variance noise of the output initial. So let me just.
You did the noise convolve with the filter.
Yeah, I'm trying to see if there is a better way, but you know, let me just do it. So it's 0 to t, right? N of t, 1. Let's say age of t1. T1 goes from 0 to t, age of t1, n to t1. Times age of capital T minus T1 dt1, right? And then that times integral from T2 goes from 0 to capital T, n of T2, age of T minus T2 dt2, right? So that's what we need to determine, because you know, I'm looking at the expected value of the square of n of when the t is equal to capital T, right? So I'm doing integration from 0 to capital T. T is 3, right? T is equal to 3. So now,
But if the expected value of n is equal to 0, at that case, expected value of n squared is equals to the variance.
correct, correct. That's what we are
So
looking
that's the shortcut.
Yeah, but you also have a product of the
Yeah, but-
integration.
Yeah.
Yeah, but that's what I just wrote here. Now, what you need to remember here is these are all linear operators. So I have T1 goes from 0 to capital T. T2 goes from 0 to capital T. And then I have expected value of n of T1, n of T2, times age of T minus T1, age of T minus T2, dt1, dt2. This follows our derivation, exactly the derivation that I had in the class. Right? Now we know what this is.
Yeah.
This is delta n0 over 2 delta of t1 minus t2. Right? So this becomes T1 goes from 0 to T. T2 goes from 0 to T. There's N0 over 2. Delta of T1 minus T2. Why? Because this is a white noise and this is essentially the autocorrelation function of the noise. And then you have age of T minus T1, age of T minus T2, dt1, dt2. But we realize that even though this is a double integral, this delta function makes it a single integral. So this becomes n0 over 2, integral when t goes from 0 to t, age of t minus t, magnitude squared t. Okay? Now, age of t minus t is our good friend. Right? Since this is a matched filter, what is age of t minus t? S of t, right? S of t. So this is n0 over 2, integral from 0 to t, s of t, magnitude squared dt. But tell me, what is this? This is yet another good friend of ours. So this is n0 times epsilon s over 2. Now, what is the energy of this signal? I have to square it, and I have to calculate the area under the curve. If I square it, I have a squared times 1 plus another 1. So it's 2a squared. Do you see that? Energy of this signal is 2a squared. So you get that your expected value of n squared when t is equal to t is going to be n0 times 2a squared over 2, which is n0 a squared. Okay? Okay, but this entirely follows the derivation that we had in class. You know, if you look at now the signal to noise ratio, it would be ES squared divided by the variance of the noise, which would be that famous relationship 2 epsilon s over n0. Okay, so let me go through some review examples here. Okay, first example is the Shannon formula example. So here's what we have. I have a digital system that looks like this. I have a transmitter, and from this transmitter I have a cable that connects transmitter and the receiver. And what I know about this system here is the following set of data. Transmit power is 0 dBm. How many milliwatts? 1 milliwatt. Line losses through this line are 10 dB per meter. So if I go 1 meter, how many times do I lose? What is the 10 dB is the loss in dBs. So how many times is the signal attenuated? 10 times, right? Another thing that I didn't mention, and I'm actually put it as number 8 here, is dB linear stuff, right? So I'm going to be testing that in more than one course. So make sure that you actually are quite familiar with that as well. The bandwidth that I have available for transmission here is 1 megahertz. And the noise figure of the receiver is 10 dB. And power spectral density of this noise is 4 times 10 to the minus 18 milliwatts per hertz.
What's noise figure?
Power spectral density of the noise. What is the noise figure? Noise figure is a measure of how much of a noise is generated inside your receiver. Here's how we understand the noise that appears at the output of the receiver. So this is a receiver, and let's say I measure the noise here at the input and the noise at the output. The noise at the input has a power spectral density kT. Right? This is your single-sided power spectral density. K is the Boltzmann's constant, T is the temperature. This is your thermal noise, just the result of the random motions of the electrons because the receiver is not on a zero temperature. So that comes into the receiver, always. Receiver itself has active devices, and there is some noise that is generated inside of the receiver that is in addition to this noise that enters the receiver itself. The way how we model that, we say, well, we're going to assume that the receiver is pure mount, that is ideal, and it doesn't generate any noise. But we're going to say that N out is going to be, the power of this N out is going to be the same one as if I assume that this is noise free, and then this noise is larger than the thermal noise. And and the factor by which we assume that this is larger, it's called noise figure. That's one of the definitions of the noise figure. So when you say that the noise figure of the receiver is 10 dB, or 10 times, what that means is that the noise that appeared here is, you can think of it as 1/10 originated from thermal noise, and 9/10 originated from the noise that's generated inside. So the total noise here is 10 times larger than what had been produced by the thermal noise alone. Practically speaking, the way how, this is all kind of relatively, I wouldn't say complex, but elaborate description of something that we use very simple in practice. In practice, what we say is the power spectral density here is kT times F. And then we treat the receiver as a noiseless. Right? So we assume that the noise at the input is F times larger than F times larger than the thermal noise alone. Okay. So let's look at what the questions are. It says, assuming implementation losses of 3 dB. So here, implementation losses. 3 dB. Determine maximum length of the cable if the bit rate of 5 megabits per second is to be achieved. So I want the capacity or my bit rate to be 5 megabits per second. So what is the maximum length of the cable that I can have to achieve this kind of throughput? So where do we start? Well, first let's take a look at our capacity formula. Our maximum data rate that I can achieve on a AWGN channel is W times log base 2, 1 plus signal to noise ratio, right? At the end of the channel, at the receiver itself. Now, if I have, this is what we call Shannon boundary. You cannot get better than that. If you have certain implementation losses, then you would put the factor here that says this is how far away from the Shannon boundary this system is operating. Now, I was asked earlier today, what are the implementation losses? They're not losses per se. There is nothing here that introduces additional loss in the signal. What they represent is your inefficiency relative to the maximum theoretical capacity. Shannon formula, which is this, we just assume without this thing, tells you the maximum capacity that you can possibly achieve on a given channel, given your signal to noise ratio and the bandwidth of the channel. What is problematic about this formula is that it doesn't teach you how you do that, right? how you, so you have to design coding and to make sure that you approach this limit. And a lot of times when we do designs, we actually fail. We're not at this limit. The distance from the limit to the actual operating point of your system is the implementation loss. It's a little bit of a, I would say, unhappily chosen term. But it's the distance between your operating point and what the Shannon capacity bound tells you is the maximum achievable throughput. So if you look at this formula here, we know what this needs to be. This needs to be 5 megabits per second. This is our target. We know what this is. This is 1 megahertz. That's the available bandwidth in a channel. We know what this is. This is what? Since we have 3 dB implementation losses, this is 1/2. We can determine what n is. What is n? N is the power of the noise. So this is going to be KT, KTB or KT. I'm kind of mixing. So let me call this B all the way around. Right, so that would be KTB times F. Everything in linear domain. All right, so this is the power of the noise. So all that, so we can use all of these to determine what the power of the signal needs to be at the input to the receiver, right? So if I invert this particular equation here, I can do something like this. 1 over gamma S over N is going to be 2 to the RB max over bandwidth minus 1. And from here, I get that the signal power needs to be gamma times N times 2 times RB max over bandwidth minus 1. Now I have everything here. So the power of the signal needs to be 2 times power of the noise is 4 times 10 to the minus 18 milliwatts per hertz. That's KT. KT at the room temperature is 4 times 10 to the minus 18 milliwatts per hertz, times the bandwidth, which is 10 to the 6 hertz, times your noise figure, which is 10, times 2, 5 over 1 minus 1. And I have a feeling that there is some parenthesis missing somewhere. So 2 to this minus this, and then this whole thing multiplied, right? Yeah. So there is a, and when I plugged in the numbers and I calculated, I ended up that this S needs to be 248 times 10 to the minus 9 milliwatts, which is minus 86 dBm. So that's the power that I need to receive to be able to still provide this data. Okay? Any questions? Are you following all of this so far? All right. So now,
Excuse me.
uh-huh.
I have a question. So why? Because the implement noise is 3 dB, so the sigma, 1 divided sigma is 1 divided 2.
Why is this 1/2?
Yeah.
It's 3 dB, minus 3 dB. Losses of 3 dB are 1/2,
Okay.
right? What is 3 dB? Plus 3 dB is 2, minus 3 dB is 1/2, right?
Okay.
So, okay, so once we know the power, I can determine the total losses. Maximum losses in the system are going to be your P transmit in dBm minus your S in dBm, which is going to be 0 dBm minus 86 dBm, where the losses in the cable can be 86 dB. So what is the length of the cable? Length is going to be
Is dBm?
or Okay, dBm minus dBm, the result is in dB.
That's, I mean, 30.
Hmm?
Yeah, it's dB.
Say again?
You want it in dB?
The difference, if you have something dBm minus something dBm, what's the result in? dB, right? So 86 dB are the total losses, so the length of the cable ends up being 86 dB over total loss dividing on 10 dB per meter. So you can have cable that's 8.6 meters long. 8.6 meter long cable will attenuate the signal 86 dB. 86 dB will turn this 0 dBm into negative 86 dBm, which when plugged into this formula would give you a capacity of 5 megabits per second at this thing. So that's one way how this question can be asked. The second way is, if the cable length is 12 meters, what is the maximum capacity, what is the maximum data rate that can be achieved? If the length is 12 meters, the total losses in the cable are going to be 12 meters times 10 dB per meter, which is 120 dB. The signal power, in this case, is going to be 0 dBm minus 120 dB. So this is minus 120 of what? What's the result? dBm minus dB. dBm. So that's the power of the signal that I'm going to receive when the signal goes through a loss of 120 dB. Now, in order for us to use this, we have to convert everything to linear domain. Minus 120 dBm, that's 10 to the minus 12 milliwatts. Right? So that's the power of the signal after going through 120 dB of loss. Now, the noise stays the same, so my signal to noise ratio is going to be 10 to the minus 12 milliwatts divided by 4 times 10 to the minus 11 milliwatts. And this is 0.025. So that's the signal to noise ratio. And then when I plug that into my Shannon's formula, I get that RB is going to be B times log base 2, 1 plus 1 over gamma, signal to noise ratio. In our case, this becomes 10 to the 6 log base 2, 1 plus 1 half, 0.025. And this gives me 17.92
How did you get?
kilobits per second. Say again?
It's KT.
How did I get this 4 times 10 to the minus, right? So the power of the noise is KT B times F. This KT, you know, I mean, you can remember both of them individually, but my advice is just for room temperature and for these kind of calculations, we kind of remember that this is 4 times 10 to the 18 milliwatts per hertz. And then in this case, so this becomes 4 times 10 to the minus 18 milliwatts per hertz. Your bandwidth is 10 to the 6 hertz, and your noise figure is 10. So this is, you know, 6 plus 1 is 7, minus 18 is minus 11. So this is 4 times 10 to the minus 11.
The noise figures in dB, right?
Correct. The noise figure is dB, but we are not confused because we know how to convert it to linear. Right? So 10 dB is 10. Right, so it's the same.
But this KT is the N naught.
Correct.
So we put in N naught, and then the gain of the figure gives us.
Yeah, this is N naught, right?
This is a not.
And this is bandwidth, and this is the noise figure. The way how you look at this is this is frequency, this is your channel, this is your bandwidth. This is the power spectral density of the noise, or all of the, I'm drawing one side, right? So it's only, frequency is only positive. So this is what only thermal noise contributes, and this is your KT. Because of the noise generated inside your receiver, you have an additional noise that is present at the output. The way how we model this, we say that there is an increase of the noise by factor of F at the input, and my receiver is noiseless. So we say, well, this is now your augmented, if you want to say PSD, and this is N0 times your F, right? The larger power spectral density. I took all the noise from the receiver and put it at the input, and I model it as a thermal noise. And then the total power of the noise at the input is going to be essentially area under the curve here, right? Integral of the power spectral density over the bandwidth of your channel. Since we assume that the channel is square box, the integration is KT times B. But if I put some filter here, then I would have KTF and then integral of h of f squared df. Remember how we do that?
But we understand this is N naught is a thermal noise.
Correct. And naught is KT. Go ahead.
Then what is the difference when you use, when you're finding out RX sensitivity, you use KTB plus F, and for
No. We
10
use,
log KTB
okay.
plus F plus
What you gotta be careful. What did we say? RX sensitivity defined in dBm is going to be 10 log of KTB plus F in dB.
Which is N naught.
Now, I can say that this is 10 log of KTBF, where F is linear, right? Or I can say RX sensitivity, now in milliwatts, is going to be equal to KTBF linear, right? It's just the different domains. One is the linear and one is the logarithmic domain. All right, so let's take a look at the next one. The next one is a pretty cool example. It's a little bit long, but you have all the details here. I'm going to skip some steps, but we have more. Because I get a lot of questions that around this the basis vectors, and I want to use this as an example to illustrate. And also, I want this as an opportunity to remind you of your good old friend, but show him in a different light. All right, so that's problem number 2. I say consider a set of signals. And I'm giving you here an infinitely many signals on a period, on an interval, interval t between 0 and some capital T. Here are my signals. x0 of t is 1 over t. X, I'm going to call them Cn of t, are going to be 2 over t cosine 2 pi n t over capital T. And x Sn of t are going to be 2 over capital T sine of 2 pi n capital T over t. And here n goes from 1 to, and so on. There's infinitely many of them, right? So I have infinitely many signals. And then the first thing is, determine the norm of this signal. Determine the norm. Danger here is that you overthink these kind of problems. What is a norm of a signal in a vector space? Take the dot product of the signal with itself and take a square root of whatever you obtain, right? So let's say, what's the norm of x0 of t?
Square root of.
It's going to be integral from 0 to t, 1 over t times 1 over t in dot product dt, take a square root, right? Just a simple kind of follow straight from the definition of what the norm is. You see here, this is 1 over t squared. Integral from 0 to t dt is a t. Divided by t squared is 1 over t. So taking 1 square root of that is 1 over square root of t. So that's a norm of the first one. Okay? Let's take a look at norm of these CNs. It's going to be again, let me just write it as Cn of t in dot product with itself, and then taken square root. So this is an integral from 0 to t, 2 over t, cosine 2 pi n t over t, and everything squared, dt. And then once you do the integration, you take the square root of that to get a norm. I'm sure you can carry out this integration. It's relatively easy. You can say 2 over t, so it's 4 over t squared outside. And then integral from 0 to t cosine squared is t over 2. Let me take one step so that you remember how you can see how you can do this integration relatively easy. So this is 4 over t squared. Integral from 0 to t cosine squared of 2 pi nt over t dt. Now, what you realize is this is an integer number of periods for this cosine, right? So to do this integral, what I'm going to do is I'm going to add sine squared here, right? Add sine squared underneath. So what's the result of the integral? No, it's going to be 0 to t cosine squared plus sine squared is 1. So the integral is going to be t. Since both of them, cosine squared and sine squared, are the same, just shifted by pi over 2. So out of this t, half goes to cosine, half goes to sine. Right? So this value of this integral is t over 2. You can do it longhand, but or you can just so this is 4 over t squared times t over 2. So t and t cancels, and this is square root 2 over t. Okay? And then the last one is x s n of t norm. You can see that this has to be equal to x c n of t and square root of 2 over t. So it's essentially the same waveform, just shifted by pi over 2. So these are the norms. The second part is demonstrate that the signals are orthogonal. That signals are orthogonal to each other. So there's a lot of demonstration to go on here, right? To do here. First, I need to demonstrate that this one is orthogonal to all of these guys, that this one is orthogonal to these guys, and then these are mutually orthogonal, and then orthogonality between these groups. Let me just write these equations. You will see that they're relatively easy to demonstrate. So first, x0 of t in dot product with s cn of t. If I write this out, this is 2 over t squared, integral from 0 to t, cosine of 2 pi mt over capital T dt. What is this integral? This is an integral of the cosine over integer number of periods.
0.
What is that? Has to be 0. Cosine, remember, is symmetric about x-axis. However much you add in 1/2 period, you lose that much in the other half. So this is equal to 0. The second thing I demonstrate is x0 of t, x Sn of t. This is 2 over t squared, integral from 0 to t sine 2 pi n t over capital T dt. What is this?
0 again.
0 again, because this is now integrating sine in an integer number of periods. The third thing I demonstrate is dot product with xcn of t and xcn of t, right? I'm taking two waveforms from this group and I'm taking the dot product between them, essentially dot product between the two cosines. So this is equal to 4 over t squared, coming from these 2 over t times 2 over t, and then integral from 0 to t cosine 2 pi n t over capital T times cosine 2 pi mt over capital T dt. This is in further equal, so cosine times cosine, this is 1/2 cosine of the sum and 1/2 cosine of the difference. So this becomes 4 over t squared times 1/2, 0 to t, cosine 2 pi n plus m over capital T, and then plus cosine 2 pi n minus m over capital T. Since I picked, m has to be different than m, right?
Professor, are we doing Cn with itself? XCn with itself?
xcn with xcm,
Oh, Cn.
right? N is different than m. Otherwise, I'm looking for a norm, right? So when I'm doing with itself, I get the norm squared.
Yeah.
So these are different. I'm taking two signals out of this batch, but they're not the same. N is different than n. Now, n and m's are integers. So this is now again integer number of periods, and this is again integer number of periods. So what's the value of this integer? 0. And fourth thing is x Sn of t times dot product with Sm of t. So this is 4 over t squared, integral from 0 to t, sine 2 pi n t over capital T times sine of 2 pi mt over capital T dt. I can rewrite this as a 4 over t squared times 1/2, integral from 0 to t. Sine alpha sine beta is cosine of the difference minus cosine of the sine. So this becomes cosine of the difference, 2 pi n minus mt over capital T, plus cosine, minus cosine of the sum, 2 pi n plus m t over capital T, everything dt. What's the value of this integral? Since n is different than m, this is again cosine integer number of periods again, so this is equal to 0. And then the last thing that I need to show is x Cn of t in x s m of t, dot product between any two, here n can be equal to m, is equal to 4 over t squared, integral from 0 to t, cosine 2 pi nt over capital T times sine of 2 pi m capital T over t dt. And this is equal to 4 over t squared times 1/2, integral from 0 to 2, to t sine of 2 pi of the sum, n plus m capital T over T, minus sine of the difference, 2 pi and minus n T over capital T dt, and the value here is what? 0. So there you have it. We have proved that everything is here orthogonal. So I have orthogonal set.
Why is it not SM?
Huh?
You did CN and SM, why not SM?
S
N can
n.
be different than M.
N can be the same as m. Doesn't matter. If you make it the same, you have 0 here, identical 0, and you have here 2n. Here you're integrating over integer number of periods, and here you're integrating identical 0. So n can be equal to n. Right? It's for any combination n and n. So orthogonal set here that consists of 1 over t, then I have 2 over t cosine 2 pi t over capital T. Then I have 2 over t sine of 2 pi t over capital T. Then I have cosine 2 pi 2t over capital T, 2 over t in front of it, and so on, right? You see how I have infinitely many orthogonal vectors. So this is now a vector space. What is the n in this space? Infinity, right? So it's an infinitely dimensional vector space. Now here's the punchline. Consider a function f of t on this same interval. So this is part C. F of t is a function on t between 0 to t. Decompose this function along this basis. Right? In general, if I decompose a function, I can, if I have a basis, I can say f of t is going to be equal to sum. When n goes from whatever 1 to infinity, you have infinitely many basis vectors here. I'm going to take f of t in dot product with a basis vector. But notice one thing. These vectors are not of a unit norm. So let's make them unit norm. So I would say, now psi k, or let me just say phi k, phi n of t, divided by norm of phi n of t. And then when I take the dot product, I make that is a coordinate times the appropriate unit vector. Right? That's the decomposition. That works always. If I can generate orthogonal bases, not necessarily orthonormal, but if these phi's are orthogonal, then I make them normal or unit norm by dividing them by their norm, and then I can take that this is a coordinate along that vector, the unit vector. So let's see this formula here. So if I say f of t is going to be, let's take a dot product with the first guy. So this becomes integral from 0 to t, f of t. Now what is my first? It's 1 over square root of t, but it's 1 over t, sorry. 1 over t is my first vector, this guy. But I need to divide by its norm, which is 1 over square root of t, to make it dt. So that's my first projection here. And I need to multiply that by the vector divided by its norm. Right? So that's my first out of this sum here. Right?
Excuse me, sir. Would you explain why it's norm, why it's not energy?
Norm is the square root of energy.
Oh yeah.
So it's
Oh yeah.
norm is the square root of energy. So that's how we define. And then I have sum. Let's bring our Cn terms. For every Cn term, I'm going to be 0 to t, f of t. My Cn term is 2 over t cosine 2 pi n t over capital T. But what is the norm? Square root of 2 over t. So that's a coordinate times the signal, which is 2 over t, cosine 2 pi n t over capital T, divided by the norm, which is this guy. And this goes from 1 to infinity. And then I have plus sum when n goes from 1 to infinity, integral from 0 to t, f of t, times 2 over t times sine of 2 pi n t over capital T, divided by the norm, which is square root of 2 over t. 2 over t times sine 2 pi n t over t, divided by square root of 2 over t. So that's implementation of this particular formula here. If I clean this up a little bit, and I'm going to use, let's say, this part of the board to do so. So look at here. This 1 over t, 1 over t, 1 over square root of t, 1 over square root of t, all that survives is 1 over t, right? 1 over t outside. So this becomes equal to 1 over t, integral from 0 to t, f of t dt, and I'm going to say times 1. And then I say plus sum when n goes from 1 to infinity. Then look at the second one. You have 2 over t, 2 over t, square root of t, square root of 2 over t. So these two multiplied cancel one of these, but one of them survives, right? So this becomes 2 over t, integral from 0 to t, f of t, cosine 2 pi n t over capital T dt. But that multiplies cosine 2 pi n t over capital T, and plus sum n goes from 1 to infinity, 2 over t, integral from 0 to t, f of t sine 2 pi n t dt times sine 2 pi n t over capital T. To shorthand notation, I'm going to say this is A0 plus sum n goes from 1 to infinity, an cosine 2 pi n t over capital T plus bn sine of 2 pi n capital T over t, where A0 is equal 1 over t, integral over t f of t, bn, or sorry, an is equal 2 over t, integral over t f of t, cosine 2 pi n t over t dt, and bn is 2 over t, integral over t f of t, sine 2 pi n t over t dt. Now, how do we call this guy? Fourier series. So what is it that we're doing when we are decomposing our function in a Fourier series? We are actually projecting our function on all of these basis vectors that I have here. This is my infinitely dimensional space, right? And you know, every function is actually can be seen as a linear combination of these basis vectors, right? So now, why is frequently I ask the questions, do these guys need to be of a unit norm? And the answer is no. See, these guys are not of a unit norm. They have different norms. Like the norm of the first one is 1 over square root of t, you know, so on. But when you do the decomposition, you have to make sure that you make the coordinates right. So the way we do that is we make in the projection on a unit norm vector, which essentially means project at this particular direction and then multiply, you know, the vector itself. And you have to make it unit vector so that the length of the vector does not change the value of the coordinate. Right? So this always works. Now, if you think about it, you know, we chose sines and cosines, but there is a possibility, or you can at least envision it, that I can have a different other sets that have this property that the signals are orthogonal, mutual. And that's I guess, I would say very common, but that is the case indeed. There are usually sets of polynomials like Laguerre polynomials or Legendre polynomials that have these kind of properties. And in general, what we have here is called orthogonal decomposition. And it's a very, very powerful tool that we use in all sorts of things, like signal feature extraction, signal compression, you know, signal analysis, and so on. So this notion of signal space and vectors in the signal space and decomposition of an arbitrary function along some preferred direction is very, very useful and common notion in a lot of areas of electrical and computer engineering. Any questions here? All right, so this one is a little bit longer. You know, it's obviously not feasible for, in its entirety, for midterm exam, but bits and pieces can be, right? I can say, you know, look at the sines and cosines and show they're orthogonal. Or I can say what is the norm of something, or what's the distance between these two and so on.
Derive the Fourier series.
Yeah. Just if you are adventurous, right? I have given you the first form of the Fourier series where the basis vectors are sines and cosines. I can actually form another set that will be this guy, e to the j n, let me just do it this way, 2 pi n t over t, where n is equal to 0, 1, 2, and so on. Or actually it's plus minus 1, plus minus 2, and so on. And you can proceed the same way. You can demonstrate that these guys are mutually orthogonal and decompose the function along these guys, and guess what you're going to get? Your exponential Fourier series. So that's yet another decomposition that we use. And I'm kind of a little bit pleased for that I derived this, because remember in communication theory, I just give you these formulas. I don't derive this at all, right? So if you have taken both of these courses, I have benefit seeing where the Fourier series are coming from. All right, so this goes early to an earlier question, 7.1. This is essentially the same as the 7.1. I say consider 4-level pulse amplitude modulation, signal that is symmetric about the origin. Most of the time when we do pulse amplitude modulation, we pick them to be symmetric about the origin. The constellation is given as follows. So this is our psi direction. Here we're talking about one-dimensional signaling, so all of your constellation points are on a single line. And let's say this is 0, and this is symmetric. A, minus 3A, and 3A. So these are your 4 points. Constellation points. And the question here, the basis vector psi of t is given as 1 over t pi of t over t. So it's a unit norm vector. It's a pulse center at the origin with a length of over t. Determine the energy of the constellation.
Average energy?
The average energy, sorry. Now, when you determine average energy, if nothing is said, you know, it really should be said. I should say, assuming equal probable distribution, you know, equal probability between the symbols, right? So I'm going to say that here. Assume that the symbols are equiprobable. Now, if that's not the case, then you have to take the probability of these symbols into account. Okay, so how do I determine the energy? Well, just since this is the first example, here's how you approach this problem. S1 of t, that's the first symbol here. Let's say this guy. It is equal to 3a times you know what, this needs to be square root of t, right? Because you have to square it and integrate it over t to make it a unit vector. So this is a 3 over 1 over square root of t pi over t over t. So that's your first symbol. S2 of t is going to be minus a times 1 over square root of t pi of t over t. And then S3 of t is equal to a 1 over square root of t times pi of t over capital T. And then S4 of t is going to be a, 3a rather, over square root of t pi of t over capital T. What's the energy of the first one? Energy of the first one is integral from 0 to t S1 squared of t dt, right? That's what we know. If I square this, what do I get? Well, let me actually do it. So this is integral from 0 to t, 9a squared over t, pi, just 1, right? dt. So it's 9a squared. So your average energy is going to be 1 over 4, because I have 4 symbols. What's the energy of the first one? 9a squared. What's the energy of the second one? A squared. Energy of the third one? A squared plus 9a squared. So if you add this 9 plus 9, 18, to so I messed up here in the notes, huh? So it's 9 plus 9, 18, and 2, 20 over 4. It's 5a squared. Okay. So that's the average energy of this constellation. The second is, what is the average power? What is the Now, how do we calculate power in general? It's average energy per time. That's power, really. So if I calculate average power, I'm going to say average energy. Where is the energy calculated? Over what distance? Over what length? T, right? So it's going to be average energy per t. So this becomes 5a squared over t. And the last part says what is the average energy per bit in this scheme here. So average energy or bit. Average energy per bit. Now, we have a 4-level modulation scheme. So how many bits per symbol are we going to be encoding here? 2 bits. So there will be 2 bits per symbol. And essentially your average bit energy, so I call this EB, is going to be your average symbol energy divided by number of bits per symbol. In this case, it's going to be 2. So this ends up being 5a squared over 2. Okay. Oh, no, I don't, because it's not the power. It's just 5a squared over. Okay. I'm actually gonna do the next one, and the last one is essentially the same as the first one we did, because that was a matched filter. As a matter of fact, it's simpler than the one we did. So let me just quickly do the next problem. That's the problem number 5. It says consider 8 PSK modulations. So how does 8 PSK look like? You have 8 symbols. It consists of a QPSK and pi over 4 shifted QPSK. So this is 8 PSK. This is 5.1 sine. And this distance here, I call it 8. This psi 1 of t is square root of 2 over t times pi t over capital T times cosine 2 pi f0 t. So those are your basis vectors. Psi 2 of t is square root of 2 over psi t over capital times sine 2 pi f0 t. So those are your two basis vectors. Obviously here we're talking about bandpass modulation because we're operating in a carrier of the frequency f0. It says determine the average energy of the constellation. So what's the average energy? One thing that we know about PSK, the average energy is the same as the energy of each individual symbol. As a matter of fact, we construct PSK specifically to make energy the same for all of the symbols. Now that's the first thing that we know. The second thing we know is what is the norm of these guys? Distance from the origin. Norm is the square root of energy. So what is the average? What is the energy of the symbol in this constellation? A squared, right? The distance is a, so the energy is the square of the norm, which is a squared. So what is the average energy per constellation? So, okay, so so average is equal to a squared. In the notes you have a little bit more work to get the same result, but since we did the previous problem, this follows straight from there. Now, the second part is determine the distance between any two adjacent points. Now, the distance between two constellation points, E and N, is essentially the norm of the difference between, right? So you take the difference between them and you take the norm. Now, you can do that in a time domain, and I suggest you do it to verify the result. But you can also do it in a vector domain. And the easiest way to do it is to treat these vectors as complex numbers. That's the third way of treating the constellation. So what I'm really looking is the absolute value of a to the e to the j 2 pi over 8 times n minus a e to the j 2 pi m divided by 8. So that's the difference between two constellation points, and then I'm going to take the norm or absolute value since I'm treating them as complex numbers. Now, this ends up being a can go outside because you can see a is common, and all I have is difference between these two exponentials. Using Euler's identity, this is cosine. You have a cosine from here minus cosine from here, plus j sine from here minus j sine from here. Do you see that? Right, this is cosine of this plus j sine, and this is cosine. So the norm becomes cosine of 2 pi n over 8 minus cosine 2 pi m over 8. Let me just say plus j sine of 2 pi n over 8 minus sine 2 pi m over 8, and then absolute value of that. Now, how do we take the absolute value of the complex number? real squared plus imaginary squared taken square root. Right? So this is a cosine 2 pi m over a minus cosine 2 pi m over a everything squared plus sine of 2 pi m over a minus sine 2 pi m over quantity squared and then taken square root. Now you can see here, I have cosine squared from here, sine squared from here, that's 1, right? I have cosine squared from here, sine squared from here, it's 1. And then I have minus 2 times cosine 1, cosine 2, minus 2 times sine 1, sine 2, right? So this ends up being a, I have 2 minus 2 times cosine 2 pi m over a, cosine 2 pi m over a, and then plus sine 2 pi m over a, sine 2 pi m over a, and then close and then 1. Now this is equal to a, let's say 2 here, 1 minus, this is what? Cosine alpha, cosine beta plus sine alpha, sine beta is what? Cosine of the difference, right? So this is 1 minus cosine 2 pi n minus n over a. That's it. And then 1 minus cosine is 2 times sine square of the half of the n. Right? So there's 1/2 missing here. So this is 2a, and then I have sine squared of pi n minus m over a taken square root. And this is equal to 2a magnitude sine pi n minus m over a. So that's the distance between any two symbols in this constellation. I think the problem asks what happens when n minus m is equal to 1, which means when n minus m is equal to 1, I'm looking at adjacent symbols, and the distance with dmn, where m minus n is equal to 1, is equal to, when I substitute 1, I have sine pi over 8, and that's some value multiplied by 2 gives you 0.7654. So this is the distance between two adjacent symbols. And then I ask, what is the distance between 2 and 6? 2, 6 becomes 2a times sine pi. 2 minus 6 is 4 divided by 8, which is the reason why I give you this, for you to check the result. 1, 2, 3, 4, 5, 6, 7, 8. So if I look at 2 and 6, what is the distance?
2a.
2a, right? So I better get 2a when I substitute in this one. So when I put 6 minus 2, it's 4. So sine pi, 4 pi over 8, that's sine pi over 2. What's sine pi over 2? 1, so this is 2a. Now what is the power of this this part of the board? What's the average power? Power average is going to be the energy divided by the symbol time. What is the energy of this constellation? The average energy, a squared, right? Because so the power is going to be a squared over t. And what is the energy per bit? So that's E. Now, if I have 8 PSK, how many bits per symbol I'm encoding here? 3. So n is equal to 3 bits per symbol. So energy per bit is going to be energy per symbol divided by 3, which is going to be a squared over 3. okay? So these kind of calculations, you know, maybe the one, if you were to speculate, you saw I did pen, I did QPSK, maybe QAM is gonna be for the exam.
16 quant.
64.
I'll go for 256.
Okay. So that's pretty much it. I mean, I have for review. It's gonna be 1 hour, 15 minutes, closed book, closed notes, formula sheet. Probably last generation with formula sheet. That's it.
Is this posted